Hey students, let me make a video solution of your exam number 3. This is a great chance to go over it and kind of study what you did, get an idea of what you did right and what you did wrong, maybe even have a rough idea of your score before I get a chance to finish grading them. But more important, of course, is to learn from any mistakes you might have made here. So let me run through this. We'll start here. It says a light ray enters a quarter circle piece of plastic at an angle of 45 degrees. Okay, so here's our 45 degrees. And remember, the angle is measured from the normal. And so the normal would be also the radius of the circle. That can come important in a little bit when we look at the second refracting piece and how they're connected together here. All right, and then it merges at 15 degrees. So let me just write over here 15 degrees. And so if we start with Snell's law, which remember says n1 sine theta 1 equals n2 sine theta 2, and 1 being where the light enters and 2 being where it exits. If we apply that to where it enters, we would say then, let me go A. Determine the index of refraction of the plastic. You would say, okay, it starts in the air and enters at an angle of 45 degrees. Then it goes into the plastic, let me just call that N, and then sine of some unknown angle, number 2, I'll just call it and label it as alpha. And so there's the angle alpha. Now, if we do that again for the exiting ray, calling this beta, we would say, okay, it starts in the plastic and is incidented at an angle of beta. And obviously there's some geometry here between alpha and beta, so we'll talk about that in a second. But just doing the physics part of there, it exits into the air, so we'll call that index 1, and then sine of 15 degrees. And of course, looking at the geometry, you can see here that we've got a nice little triangle that has alpha and beta in it, and then this angle. And that angle has to be 135 because this angle here has to be 45 because these are corresponding angles. So that means all three of these add to 180 degrees. And then if you take 135 away from 180, you get 45. And so I guess our third piece of this puzzle is that alpha plus beta is 135. Now keep that in mind. That would be these relationships would all be true regardless of what the index is. Although if the index changes, this final exiting angle could be different, which is where part B is going to come into play. It says here, if the light reflected at its critical angle instead of exiting, what would be the index of refraction of the plastic? So it looks like we need to do these calculations again for part B. It's just that in part B, let's see, the first equation won't change. It'll still be sine of 45 degrees. It'll still be n sine of alpha. Then it'll hit the other side at n sine beta. Of course, because the index would be different, the alpha and beta over in part B are going to be a little different. But then over here, if it's at its critical angle, this side becomes the sine of 90 degrees. And of course, alpha plus beta is still going to be 45. Oh, why did I do 135? Sorry about that. 45 here. Okay. So that is the set of equations that we need to solve. And notice in both cases, there are three unknowns. There's an alpha, a beta, and an n. And of course, any three unknowns problems usually involves quite a bit of math here. So why don't we do, especially since we've got this trig identity given to us, why don't we just put these first two together? And so I'll put sine of 45 equals, and I'll go n sine alpha here. And then I'll put the other equation, although I'm going to switch the order, so this is n sine beta over sine of 15 degrees, so that the n's go away, and so there's eliminating one unknown, although sadly it's the one I want to figure out. But I've got my two unknowns here. I'm going to leave this as sine of 45 for a moment, and sine of 15 for a moment, because I can think of this alpha as 45 minus beta. And then I can invoke this trig identity here. Let me just check my camera here. Okay, it's looking a little foggy from my angle. All right, now, if I go ahead and I'll just leave sine beta downstairs. But I'm going to apply this trig identity. So this would be the sine of 45 times cosine of, I guess this would be my beta, minus the cosine of 45 and sine of beta. And hopefully I won't get too far into part B here. But notice something nice happens here, because sine of 45 and cosine of 45 are the same number, that 0.707 or root 2 over 2, and which is the same that's over here. So they could all cancel off, and I just get 1 over the sine of 15 degrees here. And then over here would be cosine over sine, which I'm going to write as cotangent beta. And then over here would be sine beta over sine beta, and so that'd be minus 1. And so getting maybe cotangent of beta for a second, I would have, looks like 1 divided by the sine of 15, and then adding a 1. And so that'd be 4.864. Taking the reciprocal, this tangent beta, which then taking the arc tangent gives me beta at 11.62 degrees, which, invoking that the two have to add up to 45, give me alpha at 33.38. And I guess I didn't need to do that step, because to get n right here, I could just take the sine of 15 and divide it by the sine of beta. That's that 11.261836879. And I get an index of 1.29. So there would be part A, putting those three equations together. And then doing that all again for part B, just again, the only difference being this last part is at its critical angle. So this is 90 degrees. It looks like everything's going to look the same. When I divide these two equations like I did here, I guess I won't have this sine of 45. No, I won't have, sorry, I won't have the sine of the 15. Yeah, that'll be sine of 90. Well, maybe I should just do it here. So I would have right here, sine of 45 equals to n sine alpha. And then here, changing the order and dividing, this would be the sine of 90. Yeah, see, this is, we're going to basically replace the 15 with a 90. And then this would be the n sine beta. So the n's would cancel off, and you would just have sine 45, and because sine of 90 is 1, so it would be just like this line, you just would have a 1 down here. And then the other side would be these couple of steps, which why don't I just write it then as cotangent beta I guess I already canceled off the 45 on this line. So let me not go too far. This must be this term, cotangent beta minus 1, with the sine of 45 factored out, and then I canceled it here. So in this case, the sine of 45 would still cancel out like it did here. In fact, obviously during an exam, you might want to have just jumped right down to this line and say, all right, just replace the 15 with sine 90. That's essentially what we got here. Because if we replace that with sine 90, we get this 1 equals cotangent beta minus 1, or 2 equals cotangent beta, or 1/2 equals tangent beta. And then we can do the same set of calculations to get what is beta, alpha, and n. And so if I go inverse tangent at 1/2 would make beta 26 point, I'll just call it 6 degrees, which would make alpha 18.4 degrees, which would make beta, coming up to here, this side of the equation, which is 1, divided by the sine of beta, which is at 26.56. And so we're looking at an index of 2.24. Yay! Nice. And so again, just kind of a repeat. Hopefully you didn't take too much time in the exam to have to do these new calculations. They kind of fell from this one. But the real thing is, would you recognize then what, when talking about the critical angle, this secondary refraction index is 90 degrees. This one here is kind of the giveaway. So it wouldn't be part of this one, although that's part of your calculation, because it still enters at 45 degrees. All right. Well, I hope that went well for you. I think that might be maybe even the hardest one. I don't know. But it's got some geometry and trigonometry as well as the physics in there. All right, let's try the second one here. And so, yeah, it keeps getting out of focus. I think there's a little bit of something on the lens here. Let's see if that helps. Maybe it's focusing on my hand in that case. All right, so here we go. A photographer is taking a picture of a tree, and it's an 8.7 meter tall tree. And the image of the tree needs to fit on the film, which is 35 millimeter film. And also a little hint here is that the light must hit the film. That means we must have a real image, and that must mean Q is greater than 0, because we have to have the energy actually going to the film, or in today's camera is a CCD array. So there's a little bit of physics there where we can't just blindly put in the math. The tree is 25 meters from the lens. What is the focal length? How far is the lens from the film? And then a little interesting one here, but let's do A, and I would even say A and B kind of go together here, because we know that 1 over P plus 1 over Q is equal to 1 over F. And this was the neat thing about our geometric optics is if you're willing to remember a number of rules and sign convention rules, so Q greater than 0, this equation works for all of the mirrors, all of the lenses, and so it's just really nice to work with that equation. The other nice equation is that the magnification, which is the height of the image to the object, is negative Q over P. And that's where we're going to invoke our little bit of physics, because we know the height of the object, the tree itself, is 8.7 meters tall. And the image we want to be, no more, but as big as we can take the picture so we can get the highest resolution. So we want it 35 millimeters tall. And so in meters, that'd be 0.035 meters. Now, the one that, again, maybe not so obvious, is we want it to be upside down because we need Q to be positive, and that only happens with the convex lens. And so if you have a convex lens, you have a tree, it'll make a image that, remember, is smaller and upside down if you're more than twice the focal length. And so twice the focal length makes a real image, makes it upside down, and makes it smaller than the actual object itself. And so that's where I guess I'd say the physics piece kind of comes together on all this. Okay, so with that in mind, I'm going to invoke that the image is upside down and is a negative. So then I get negative Q over P, which is 25. And this allows me to answer, I guess, the part B, the Q, really. It doesn't exactly say it. That's another part that you've got to interpret here. But how far is the lens from the film? This would be the Q value. And so Q equals what? And so, grabbing the calculator here, I'll just mentally cancel out the two negative signs. And this is 0.035 divided by 8.7. So there's the magnification. And in fact, I might write that down. 0.00402. Okay. Then I will multiply that by 25, and it looks like I have a 0.101 when it rounds up meters, or if you like, 10.1 centimeters. So there's my Q value. And of course, the other one, A, is the focal length. So here we can go 1 over 25 plus 1 over 0.101 equals 1 over the focal length. And so 25 reciprocal plus, well, let's do the last answer. Last answer, reciprocal, enter, reciprocal of that. And we are looking at 0.100 meters. And so not a surprise if you remember kind of our setup here that, again, objects that are more than twice the focal length will be upside down and smaller. And the further away they are, the smaller they get. And we're looking at a pretty significant, reduction. That's why I thought I'd write down the magnification factor here and say, okay, how much smaller did this one actually get? And it got a lot smaller. So we know that the distance of the tree is quite a bit more than the distance between the lens and the film, or the lens and the CCD array. Really, really small. Of course, just holding a camera, and that there's not that kind of, couldn't possibly be much more than this. And of course, if your camera these days is your iPhone or a phone, it's got to be really close together. Anyways, but the q then does have to come out to be a little bit higher. In fact, if the object was infinitely far away, the f and the q would be exactly the same number. And so we're not infinitely far away, but 25 meters is pretty far compared to the 0.1. And so it's not a surprise that these are almost the same and that the q is just a hair more than the f. All right, now maybe a little harder one here is the c, because you can see in the description here of object and image and focal length that if one changes, certainly another one has to change. And the focal length is determined by the lens, what it's made out of, and the curvature of it. So that doesn't change, and so you have this interplay here. And so when something moves, let's say further away, well, let's just say closer, because that's what this one is going to do. You're going to get closer to the tree. So if this gets smaller, this one has to get bigger, so the two, remain not the two remain a constant, but this relationship, the 1 over p plus 1 over q remains a constant. So this gets smaller, this gets bigger. And so my q should get bigger. And so there should be some kind of mechanism that's going to separate the lens from the film. And in an old-fashioned camera, you'd roll the barrel and move the lens and focus it with your own eyes and see where do I have to focus it. These days, the autofocusing does it for you, but it's got to move that spacing a little bit, and that's what this one about. It says if the photograph is now shooting a video and is walking towards the tree at a rate of 2 meters per second, what is the rate of the autofocus computer moving the lens in order to keep the image? Okay, and the image of the tree in focus. And so here, give you a little hint that if you know the relationship of position, which we do, we can get the relationship of velocities by taking the time derivative. So let's do that. And if you view this as p to the negative 1 power and q to the negative 1 power equals some kind of unchanging constant, when you take the derivative of p to the negative 1, you get a negative 1. And then you subtract 1 from the exponent. That would be p to the negative 2, which I'll just put downstairs. And then the chain rule would give you how does p, sorry, not q, p change with time. And basically the same thing here. So negative 1, q squared, dq, dt, and then a derivative of a constant is 0. And what we're looking for is really this dq dt. And again, like part A, this is where we're going to have to put in our own, I'll call it brain power, and say, what are they looking for in this? They didn't say find dq dt, but they are asking you to find the rate at which the lens is moving, the computer is moving the lens in order to keep it in focus. So if you solve for this, imagine it moving it to the other side, you still would have a negative 1, and you still would have a p squared and a dp dt from this term. Move it over to here, that would become positive, and then if you move the q squared back over. So now if you have the p and the q and then the dp dt, you can solve for the dq. And another reason it was kind of nice to write the magnification is the magnification is technically a minus q over p. But if you square that, you get a positive q squared over p squared. And that's what I have right here, a q squared over p squared. So I can just write that as the magnification squared. And so that would be 0.0402 squared for that relationship. And then the dp dt, this is the rate at which the object is moving. Now, at least relative to the lens, because technically the object, the tree's not moving. You, the video or videoer, you're the one who's moving towards the tree, if you will. And so we're moving at a rate of 2 meters per second, okay? But we are moving towards the tree. So I guess technically we need to put a negative here because our P is decreasing. Remember, P is that measured distance. Which actually is great because that negative and that negative make a positive. And we said earlier then if this number gets smaller, this has to get bigger. So our dq dt should be getting bigger because we know we're getting closer to the tree here. And now just putting in our numbers, if we take that magnification of what do we have, 402, and square it, and then multiply it by 2. Oh, my bad. There was 2 zeros there. 2 zeros. Let me try that again. 0.00402 squared times 2. All right, and so I get 3.23 times 10 to the minus 5 meters per second, which is such a small number. Might be nice to take the first 10 to the minus 3 and call it a millimeter. And so, very, very small rate, something that can easily be done electromechanically, not just mechanically. And so it's kind of nice with our new phones. We don't actually have like the old camera where the motor actually, and the lens actually moves a significant distance. We don't even hear it. We just pass an electrical current, and the electrical current changes the distance for us. So that's nice. All right. Well, I think both of those were hard. Let's then keep going because, like I said, surprisingly, it wasn't my intent, but looking over this, I think that the first two might have been a little harder than the rest of them, with maybe 4 being the easy one. But let me read this one here. So this one says, light with a wavelength of 600 nanometers passes through a Young's double slit experiment. The distance between the slits and the distance between the screen is, what is the distance from the center to the second bright fringe? Okay. So I'm hoping you remember this d sine theta equals an integer number of wavelengths. And so if my double slit looks like this, and the separation is d between them, and here's the center, and up here on the screen is a distance y. We're looking at the light here, the second order, so m is going to be equal to 2. This is L. Because we could say that then sine theta is roughly the same as theta, which is y over L equals to m lambda, or put another way, y is equal to m lambda L over d. And that's what they're after. What is the distance to the second bright fringe? So this would be a 2. This one would be 600 nanometers. Let me write it in meters. The length to the screen, let's see, distance to the screen, 5 meters, okay. And the distance between the slits is 0.045 millimeters. So we will be left with meters. Good. And let's see what we get numerically. So 2 times 600 times 10 to the negative 9 times a 5 divided by 0.045 times 10 to the negative 3. And we get I'll go 0.133 meters up the screen. All right. So hopefully that one was pretty straightforward, because now part B gets a little harder here. This is going to put together our geometric optics and our double slits, and the idea that if you ever have two optical elements, the image created by the first optical element then becomes the image for the second one. And here's why I say that. It says, now, if you put a diverging lens with a focal length of negative 1 meter, and it is placed midway between the slits and the screen, what is the distance to the second bright fringe? Now, okay, well, if this was our setup before we put the lens, and let's just say the second bright fringe was right there, and we put this diverging lens here, notice it would take the light and spread it out. So this would be putting it somewhere further up the screen. So at least conceptually, hopefully I'm going to get a number bigger than this. Okay. Now, conceptually, and maybe changing color here, when the light comes here, and so we'll call this the object, and hits my lens, there will be then an image. In other words, this observer, the screen, will be seeing the light as if it came from the image of this lens. So if this distance here was 5 meters, and we now have put it halfway, so this is 2.5 meters each. I think that's what it says. I don't know if it's placed midway, yeah, between the two slits. Then we're going to get an image. Now, if you kind of remember our setup for our diverging lens, we said that the diverging lens is the same as the diverging mirror. That's the convex mirror. So the concave lens and the convex mirror behave the same. And if you remember, the convex or diverging mirror, as well as the diverging lens, always made an image that was virtual. So it's going to be over here somewhere. So the screen is going to say the slits are over here somewhere. And they are shorter in distance. And also makes them smaller. So I'm going to put in red kind of what the screen would perceive. And so the screen is going to perceive a double slit that's closer and closer in distance and closer in slit separation. And so I need to find those. You might say something like this, that this new distance is going to be the Q from the lens. And maybe I should say it's the absolute magnitude of it, because keeping our sign convention, this should be a virtual image, and it should then be a negative. And so I guess I would say my effective length now between the slits and the screen, it's really the image of the slits and the screen, is really going to be this 2.5 meters plus the absolute value of Q. That's kind of the key to this problem. Then it's going to be the same calculation. Of course, the D is going to change, and so D is this magnification, if you will. And so I would say the magnification, which is the minus Q over P, is the effective D. That's how high the image is compared to the what I'll call the real, an honest D. And so that's the crutch of this problem, is really saying, what is the new effective distance between the slits because they have been reduced in their size. In other words, their magnification is less than 1. And also, the slits have been brought closer to the screen by this, and so we'll call it the effective length here. So maybe I'll put in this diagram the effective length and the effective distance between the slits. So I need to do this 1 over P plus 1 over Q equals 1 over F calculation to figure out what Q is. And since, well, let's put it in the 1 over P, and then P would be how far the object is from the lens. So that's the 2.5 meters. The Q is what I'm trying to find. And the focal length is then a -1. So I guess in my case, I'm going to go, I'll just call that -1. And subtract off the reciprocal of 2.5. That should give me a 1 over Q. Invert that, and that should give me my Q. So, as we mentioned earlier, the Q should be a negative number, so it is. And, of course, then that gives me a magnification, which makes things smaller, so magnification should be less than 1. And it doesn't invert it. I don't think I mentioned that it made it smaller and upright, but that's what the diverging lens or the concave lens or the convex mirror do. They make things closer and smaller, but also virtual. Okay, so this minus Q over P then would be I guess a negative of my last answer. So there's negative of Q divided by my P, which gives me a magnification of about a 2.857. Oh, that's that famous sequential that continues. That must be 2/7. All right. So there is the magnification, and that allows me then to come back to our earlier statement. And as long as I have the magnification in here, let me calculate the effective D here by taking the magnification and multiplying it by the D. The D was 0.045 millimeters. So now this is going to be a 0.01287. Yeah, okay, let's go 6 millimeters. So there's my, I'll again call it the effective D. And then my effective L would be the 2.5 plus the absolute value of the Q, so 0.714. And so that's going to be 3.214. So again, what the screen is going to perceive is as if the real slits and the lens aren't there. It's just going to perceive where the light appears to be coming from that lens, which is the image. And so we can mentally just get rid of the lens and get rid of the original slits and look at the image of the slit. That's what the screen is going to see. So that's why I keep calling it this effective L and this effective magnification, which is, I think, why this B can be a hard problem, because we're putting together, two different chapters. Although we talked about it in lecture and whatnot. So, and I think your author gave an example, and I think I did too, of this one. So I hope this went well for you. But now we can go on and just kind of plug this in. This would be M times L, and then, or lambda times effective L times effective D. And so this would be 2 times 600 nanometers times 3.214 meters. I guess I didn't put meters here. Divided by 0.01286 times 10 to the negative 3 meters. So that's one of the meters cancel off, and we're going to be left with so many meters. And hopefully, as we said earlier, because it diverts out, it's going to be a bigger number here. So let's see what we get mathematically. 2 times 600 times 10 to the negative 9 times 3.214 divided by 0.01268 times 10 to the negative 3. And, at least 3 significant figures. It's 3/10 of a meter. Yay. All right. That was a tough one. So I'll say it again. Hopefully A was pretty straightforward to you. B, as you can see, was a bit involved. All right, on to 4. And I think one of the reasons 4 was a little more straightforward is because it doesn't have a part A and a part B. And I think part of the reason I was thinking about it is I saw how many parts I gave for 1, 2, and 3. So I go, well, let's make this a shorter one. And it's a resolution one. It's kind of talking about the first picture of a black hole. And so for the first time, we've got direct pictures of a black hole, and it was relatively recent. But even though black holes are big and separated by a huge distance, they're so far away that because of diffraction we talked about, they blur together, and they're really, really hard to see. To add to it, you usually can't see it in the visible light, so they use radio waves. But the way it was described as difficult as seeing an orange on the moon. So let's do that calculation. And so if you're looking in the visible, it says, it is said that it's equivalent to taking a picture of a 7.8 centimeter orange on the moon. What size of lens, the diameter, would be needed in order to resolve? That's to see an orange on the moon. So let's just say you really did want to see an orange on the moon. You would want to be able to resolve it. And our minimum resolving angle, remember, is this lambda over diameter. And there's an extra factor of 1.22 that we do for circular apertures. And as I mentioned in the lecture, there is no 1.22 for what we derived. We said the minimum, and we derived it for a slit, would be lambda over A. So if you don't have the 1.22, that's not a big deal. It's a little more accurate with the 1.22. So hopefully you did. Maybe I'll just call it a small 1 minus 1 point if you drop that off, because I've been kind of minimizing the effect of the 1.22 just because it wasn't derived, and the mathematics is a little beyond the scope of this class. And it, of course, comes out to be almost the same. But hopefully you do have at least this, either a lambda over A or lambda over D. Now, the other part of this is this minimum angle. And so if you're looking at, an orange, and you're trying to resolve the orange, you need to see the difference between the top and the bottom of the orange. And so this is your angle theta. And when you're talking about huge distances like this, whether you consider it a straight line across the orange or part of an arc that has a radius from whatever you're looking from, and in this case, we're looking from Earth to the moon, this being 384 million meters. These are nearly the same. And of course, the reason that's nice is because the definition of theta in radians is this arc length, which if we take it to be the size of whatever we're looking at, so this would be the, and I'll write it in meters, 0.078 meters for the height of the orange. and the distance is 384 million meters, we need to resolve within this angle. So that's what needs to go over here, the ability to, resolve that particular angle. Okay, so taking this number, 0.078, and divide it by 384 million. 123, 123. We're looking at a really small angle of 2.03 times 10 to the minus 10th. And of course, that would be measured in radians. All right, so taking that over to here, the diameter would need to be 1.22 times the wavelength. And if we're going to watch it or take a picture in the visible light, I'll just get roughly the middle. I guess 550 is a little closer to the middle. And then this 2.03 times 10 to the minus 10. This will answer our question about what does the diameter need to be. So 1.22 times 500 nanometers divided by this resolving angle, which is the last answer. And we're looking at about 3,000. This says 3,003 meters. And so you can see why we don't have the ability, really. I mean, I guess we can make a telescope with a lens that's 3 kilometers in diameter and take a picture of that kind of a revolution on the moon. It might be easier just to send a probe closer by and take a picture and send the data back, which is what we do. As we map out the moon, we just send up satellites to orbit and take pictures. Now, a small subtlety is kind of a fun thing. You could do something like this, and this is kind of what we do looking back onto the Earth, is instead of making a telescope with a completely rounded diameter, you might just have a section of the mirror, another section, and another section. And each of those sections then are funneled through our optics system. And so you don't really have it 3 kilometers in size, but you have the equivalent of it because you're collecting light that is 3 kilometers apart. And you put these here. Now, I'm not saying we make these things 3 kilometers, although I guess we do when it comes to radio telescopes. In fact, much more than that. We put one radio telescope in the northern hemisphere and one in the southern hemisphere, and we have basically the diameter of the Earth is the size of our lens, if you will. Of course, then the wavelength is much bigger, so you need a big diameter to see any decent resolution. Which, by the way, is how they did these black hole ones. But the visible is certainly much more complicated. But looking back on the Earth, the spy satellites will do that. This might be the satellite, and then they'll send out a long arm this way, and a long arm that way, and a long arm that way. So they don't really have a big lens as much as they have the equivalent of a big lens. And so you have the same resolving power. Now, you don't collect all that light, so you're missing this part of the lens, so you don't have the light collecting ability as a full lens. But usually, like I said, a satellite looking down and mapping the Earth or mapping the terrain or spying on different countries and seeing, what their military is doing, the amount of light is not the problem, it's the resolution that's the problem here. So, and of course, looking back on the Earth, you're not looking at this enormous distance the same. So you're only looking at a couple hundred miles back down from orbit down to the surface of the Earth. Anyways, I digress there. So let me say, there's the answer to 4, and I hope that one went well for you too. And the last one, and of course, out of chapter 38, has to do with our polarizing filters. I guess we start with unpolarized light is passed through 2 polarizing filters, and its intensity is reduced to 20%. Now, let me read that carefully. It didn't say reduced by 20%, is reduced to 20%. Okay, as it passes through both filters. What is the angle between the 2 transmitting axes? So if you kind of remember this, we can kind of represent unpolarized light like this, and then after it goes through a Polaroid, the other side, it's now polarized. And if this was the intensity before the polarizing sheet, about half of the light gets through. So right there, we're already reduced to half. That's why reduced by 20% would be impossible. You're already going to lose half of it through the first polarizing sheet. Then if you go through another polarizing sheet where there is an angle theta, this intensity, I'll call it theta 1, or I1, is reduced. So I2 is equal to I1, reduced by cosine squared of the angle between the polarized light and the transmitting axis. And of course, the direction of the polarized light is the transmitting axis there. So this theta would be playing a dual role. It's the angle between the polarized light and the transmitting axis. But it also, because the direction of the polarization is the same as the transmitting axis, it's also the angle that we're after, because it says the angle between the 2 transmitting axes. Now, continuing on with this calculation, here we could put 1/2 I naught cosine squared theta. And the total intensity, they said, is reduced to 20% of its original. So I'll say that's 0.2 times its original. So the original cancels off, and we can even move the 2 from the downstairs up to here and get a 0.4. And so we can answer this question: what is the angle between the 2 transmitting axes? So let me first take the square root of the 0.4. And so that's cosine of theta. Let me go then inverse of the angle. And we're looking at about 50.8 degrees between the 2 transmitting angles. And I'll say it again, also the angle between the transmitting and the direction of polarization after it gets polarized, because at first there is no direction, it's unpolarized. Now, I keep saying that because B gets a little bit harder, and you do want to make sure you understand what the theta here is. Because listen to this. It says, if the light hitting the first sheet is unpolarized. Okay, so in other words, you would have a picture where you have an intensity of I naught and you have it polarized. And I'll just draw it upward. And then you run it through the first polarizing sheet. What's going to get to the other side, so I'll call it intensity 1, is going to be what you start with times cosine squared of, and let me not use a theta here, but it's going to be the angle between this polarization and this transmitting axis. So let me just call that alpha. And interesting then is now the direction of polarization is the direction of the transmitting axis. Because then when you go through a second one, so let me just come back to the question here. It says if the light hitting the first sheet is polarized instead of unpolarized, and the light transmitted through the two filters is reduced to 25%, where the angle between the two sheets has not changed from part A. Okay, so let me just maybe draw the second sheet. And this hasn't changed. So the angle between the polarized light hitting this one is still theta equaling 50.8 degrees. So the intensity over here, number 2, is number 1 times cosine squared of 50.8 degrees. And this is, again, why I said be careful what we mean by this angle theta in here, because we got to do it twice, and it's the angle between the directional polarization and the transmitting axis. And so the first time I'm just going to call that an alpha, and then the second time has to be a theta. And of course, then what comes out the other side would be in the direction of the transmitting axis. So when we get to the question here, what is the total angular change of the polarization of light? I hope you'll see that the first one changes its angle by alpha, and then the other one an additional theta. So alpha plus the theta is what I'm after. Although I guess technically it could have been theta the other way, so it could be the difference between them. So it could be alpha minus theta. So maybe we'll do both of those. But I won't worry about, both of them. If you get this, that's kind of the focus, is to realize all these angles involved and that the total polarization is the sum of these two. All right, so this final equation right here, number 2, would then be the original intensity times cosine squared of alpha times cosine squared of 50.8 degrees. And of course, they said this time, 25% of the original. So the original would cancel off, and you have 0.25 equals cosine squared alpha cosine squared 50.8. And that should allow us then to calculate what alpha is. So I'll take the 0.25 and divide it by cosine of 50.8 squared. And that should be cosine squared of alpha. So taking the square root of that should be cosine alpha. And then taking the arc tangent of that, I should get 37.7 degrees. So alpha plus theta is 88.5 degrees. So we've rotated the polarization angle by almost 90 degrees. So it's almost 90 degrees compared to what it started at. Of course, the intensity is only 25%, but getting something out of it was really quite nice. Now, I suppose I should do the difference, and I guess we can do the difference either way, but I'll do the, 37.7 and subtract off the 50.8. So the 13.1 in either direction, depending on how you order them, is fine also. But hopefully you did at least that, the 88.5 degrees. All right, and that's the whole exam. So, like I said, hopefully you were able to check your answers and see what you did wrong and see what you did right, learn from your mistakes, and be that much smarter. All right, take care, everybody.